The BSides DC 2017 videos are brought to you by Threat Quotient, introducing the industry's first threat intelligence platform designed to enable threat operations and management, and Data Tribe, a new kind of startup studio co-building the next generation of commercial cybersecurity, analytics, and big data product companies.
Well, hello folks. My name is Ajit Thyagarajan. I am at Atomic Mole, and I'm going to talk about PATRIOT, which is perceiving advanced threats by rogue IoT. Here's the obligatory about me slide. I'm currently the CTO at Atomic Mole. We are a small cybersecurity company doing IoT threat detection. I'm a big fan of machine learning. I'm not a machine learning data scientist myself. My background is more in network protocols. Prior to Atomic Mole, I was at a company called Fidelis Cybersecurity. You might have seen a presentation from Fidelis just earlier today. There were a couple of data scientists over there talking about machine learning again. But I ran their network sensor group, everything to do with protocol analyzers and so on. And a very long time ago, I worked a lot with internet protocols. I did a lot of work with NTP, Network Time Protocol. My advisor in graduate school was the guy who invented NTP, so I got a chance to work with him. I also worked a lot with multicasting. Internet multicast was very big in the late 90s. Everything from IGMP to DVMRP to PIM, sparse mode, dense mode. I don't know, I'm telling my age over here. But yeah, I was working a lot on those protocols in the late 90s as well. Okay, that's a little bit background on me. So let me just give a quick overview of what I'm going to be talking about. So I'll give you a quick state of the union on IoT, what's happening in the world of IoT today. Next, I want to sort of talk a little bit about what the issue with detecting IoT is. Is there IoT in my network in the first place? So we'll talk a little bit about that. We'll then go into talking about how we detect IoT threats. And just a brief side note, initially when we were talking about PATRIOT, since we were talking about detecting IoT in the network, the algorithm that we came up with was IDIOT, but IDIOT was probably not such a good name, so we migrated over to PATRIOT. I will try to give some examples using Bro. How many of you all here use Bro or are familiar with Bro? And how many are not familiar with Bro? Okay, a few, okay. Again, machine learning seems to be like the hottest thing in the planet today. So I'll use some basic machine learning techniques on how we can use basic ML techniques with Bro data to detect and to identify and detect threats with IoT. Okay, so it'll be interesting from that perspective. So IoT is a huge phenomenon that's happening right now. Depending upon whose estimates you believe, there's supposed to be like 9 billion IoT devices out there today, 36 billion by 2025 or so. Huge revenue opportunity, 470 billion, and around 5.5 million new devices on a per day basis. Again, this is the entire world of IoT. IoT is also enabling a lot of smart automation. Apparently, 47,000 jobs were directly or indirectly created by IoT in the country of Spain by them moving to smart cities, for example. And that last number there is the most recent update I got from Nest saying that they had saved 13 gigawatt hours thanks to their Nest thermostats. So yes, IoT is becoming a fairly large phenomenon today. But the problem with IoT is this whole security thing. So today, we had 152,000 devices participate in the last Mirai botnet attack, a few months ago. 70% of IoT devices are supposedly vulnerable. If you go to the IoT village over here, the guys will say it's pretty much every device. Because I had a conversation with them and I said, okay, you've got D-Link cameras over here. Do you have any D-Link device that is not, vulnerable? And he said, no. So yeah, highly vulnerable set of devices that are being sold out there. There were nearly 8.5 billion devices potentially affected by the most recent Blueborn Bluetooth vulnerability. This was literally 3 weeks ago. Fortunately, most of the devices got patched, including your phones if you subscribe for automatic updates. But there were a lot of unpatched devices as well out there. So if you have this Bluetooth capability on your IoT device and you know that you haven't patched it, I recommend that you do. And the other big issue with IoT is just visibility in your network. A lot of administrators are just not sure how many devices there are in my network in the first place, and so they maintain a very tight control of what they can and cannot implement in their enterprise. But some of them are more lax, and for them, the ability to gain that visibility is very key. And of course, there's a huge problem with personnel. We just don't have enough people to sit and help with analysis and with security issues. Some other vulnerabilities that were recently discovered was if you were at BSides Charm, there was a guy who showed how he could hack into a pressure cooker. And of course, you heard about the voting machines that got hacked at DEF CON. That was in the news as well. And just recently, there was all the access camera. You could put a devil's IVR malware on that as well. So 249 out of the 251 IV cameras were affected. So anyway, big problem with IoT from a security perspective. So we talked about this high-profile IoT attacks. These were the large number of devices that participated. We had the Mirai botnet. There are still a lot of DDoS attacks that are going on, depending on which magazine you read. And in my opinion, there is another major attack that is sort of waiting to happen. Okay, so I think this is definitely going to happen in the near future. So what are the key IoT challenges? And the reason why IoT is such a security problem is that you can't put any antivirus on it. So you have all these endpoint companies that claim that they have AI and the next generation malware detection capability, but you can't put any of this on the IoT devices because they're closed devices. The second thing is they produce little or no logs. So you can't take your favorite SIM tool and aggregate all that data and look for these threats. Is my IoT device compromised or not? So those are the two major issues that companies face from deploying IoT. And of course, if you're a lax company and you allow for devices to be brought in and randomly connected onto your Wi-Fi network, then you have a BYOD problem as well. So those are some of the key IoT challenges. So from IoT security and what do you need to do? You have to sort of consider yourself hacked, in which case you need sort of the tools to detect whether any of my devices are hacked or any of my endpoints are hacked, and you need to have multiple layers of defense as well. There are a lot of solutions out there that are perimeter solutions, so they monitor your traffic going in and out of the organization. Highly recommended that you get one of those perimeter solutions. And then now there's a flood of edge detection solutions as well, solutions that will look at your wireless LAN. There's WLC, wireless LAN control protocol. They will monitor all the logs from those protocols to tell you whether you have authorized devices, unauthorized devices trying to do IV attacks on your network and trying to gain access, et cetera, et cetera. So you need a combination of both perimeter and edge detection in order to sort of, make sure that your life is sane going forward. So one of the things is, so yes, you need a lot of monitoring and visibility tools in order to manage IoT devices if you are deploying IoT. So from a network administrator's perspective, what are their wish list items? So the first thing is they would like to have some sort of device management capability. So which means that they want visibility into what is connected into my network. And there are some tools out there like your Qualys and your Nessus scanner and so on. They want access control capabilities. They want to make sure that no rogue devices are accessing your network. And then once you have that sort of figured out, then they need the ability to figure out, okay, are these devices that are connected to my network posing any risk for me? So I need to understand what kind of vulnerabilities they have. Usually, if you run down the OWASP top 10 list of vulnerabilities, everything from are these devices using insecure communications? Are they sending passwords in clear text? Those are sort of simple things that you would like to get some idea of before I deploy my devices. And that also gives you a risk profile on the devices in my network. Then once you have that, then you want to go to the threat detection component where you want to see if these devices are potentially compromised or not, okay? And if they are, what can I do about it? Can I get notified? And how soon can I get notified? And of course, there's the whole anomalous behavior aspect, which is, okay, is there, even if I don't know if whether it's compromised or not, can you at least tell me if it is behaving abnormally? And if so, that may lead to some sort of a compromise. That may be some sort of a compromise. And then finally, everybody wants instant remediation, which is you either quarantine that device or you prevent it from communicating altogether. So again, that's a hard one. It usually requires either access to the device itself, or you need to somehow write some rules on your firewalls to sort of block that communication. Okay. So let's go on to the IoT identification phase now, which was a part of that whole device management space. And we'll talk about why IoT identification is important in a little bit, or rather it'll become clear. First, let's figure out what is and what isn't IoT in my definition. So in my definition, IoT is not IoE, okay, which means that a lot of people think that, okay, anything that's connected to the internet is an IoT. Well, not quite. We want to distinguish between devices that exhibit autonomous behavior and devices that are sort of controlled by human behavior. So laptops, desktops, mobiles, gaming platforms, they have direct user input into them, and therefore their behavior is governed by user input for the most part. Whereas IoT devices like your Nest thermostat or your wall switch will react to a user input, but then for the most part operate autonomously. So that's a key differentiator. And this also becomes very clear if you look at industrial automation and sensors in the county for collecting rain data and weather data and so on and so forth. Okay, and by the way, that definition of exhibiting autonomous behavior came from network world. Okay, so they didn't go with the whole IoT equals IoE. So what are the characteristics of these IoT devices? So IoT devices, first, they generally generate a few short packets, per device. Again, I'm just giving you some sample characteristics. It's not. Every one of these doesn't apply to every single IoT. These are just sort of approximate characteristics on a generic scale. They tend to have low duty cycle traffic patterns. That means maybe a long duration between transmission bursts. Like I may send out sensor data every hour or so. I have a Nest thermostat at home that sends data out literally every hour or so. And the traffic patterns have small statistical variations with them, which means that there's a lot of periodicity involved in these traffic patterns. And the other thing, which is actually a key characteristic, is that they tend to be uplink dominated. So that means that the uplink volume tends to be higher than that of the downlink volume. And also, and this is another key characteristic, which is that they tend to have a low destination count, which means that if you look at the number of unique destinations that they communicate with, that tends to be a fairly small number, and also a fairly constant number. So it's a constant small number from an IoT perspective. So these are sort of characteristics that we will use to identify IoT devices in your network. So one thing that sort of came into my mind early on was, can we just do an IoT lookup in some sort of a database? I mean, you have feeds for threats, for malware, for bad domains, and so on. And we tried to look for a few sites that had a list of IoT devices, and we found some of these. The third one was interesting. They claimed to be the dominant site for all IoT devices, except that they only had less than 100 consumer-grade IoT devices. So if you go to iotlineup.com, you can see what those 100 are. And obviously, it's not going to work. With 5.5 million devices being added per day, that's just way too many devices. So you really need automated detection. Okay, so that's the key requirement here. So enter Bro. So we can start using Bro. Bro is the previous speaker also mentioned Bro. Bro is a network monitoring software. You can run it on a VM. There are appliances available as well. And it essentially collects session metadata from all of your traffic. And depending upon where you place your Bro sensor, you can either collect session metadata of devices communicating with the internet, or even inside your network as well. So it really depends on the position of your Bro sensor. So the idea is that if you're trying to do IoT detection using Bro, you try and get as much good data from your Bro sensors in the network, and then maybe you can identify which one of those are IoT devices inside that. You may already know some of the IP addresses assigned to those IoT devices. Maybe they have a DNS name inside your network, and that's one way to identify them. And then you can write some rules to detect each type of IoT in your network. So you may say that, okay, if it is this IP address, and if it is communicating with these endpoints, then boom, that's an IoT device. So you can do a whole bunch of if-then-else statements there. But that's hard. That's hard to scale, and it's hard even if you generalize to some of the characteristics that we gave earlier. So what you can try and do then is, what if you were to introduce some machine learning into this whole process? So if you were to look at IoT detection using Bro and machine learning, now your procedure looks somewhat like this, which is you still get as much good data from your Bro sensors in the network. You can identify your known IoT devices in the network using the techniques that I mentioned before. But now what you do is, with machine learning, is you start labeling your traffic. So you start labeling which of my devices are IoT and which are not. And then you run a preprocessor on that data to see what are the relevant features. And then you apply some domain expertise to get what is called engineered features, and we will talk through these in the next few slides. This is just a summary. Apply some suitable machine learning supervised algorithm to the data, and then you see how good your results are. Okay? And of course, at the end of it, you have to continuously kind of tweak these parameters to see if you can get better results. Okay? So what does Bro data look like? This is sort of just a dump of some Bro connection log data. It has multiple fields, usually source port, destination port. These are all TCP connections. And yeah, okay. So as I said, your first job is to figure out which one of these. Oops, sorry, no, it got messed up here. It's not displaying properly, but anyway, you will see some of these IP addresses are IoT and some are not, and your idea is to just go through that. You can, once you figure out which IP addresses are IoT, you can just run a little script that will add that label into to all of your data. Okay. So the next step is to run a preprocessor which extracts those features that are relevant. So if you just run a preprocessor on the raw Bro data, you will get the preprocessor will go through, munch through all that data, and then tell you, okay, you know what? These are all the relevant features that I think you should consider. So this is what we did. We chose univariate as one of the preprocessors, ran it, and the stars over there kind of tell you what the relevant features are. But there's not just one preprocessor. There are actually like tons of them out there. So what we did is ran it with all of them. So there's univariate, there's PCA, there's Lasso, there's a whole bunch of them. So we ran it through every one of them, and then we sort of took a statistical average. We averaged out all their responses and sort of came up with that line at the bottom that said, okay, here is an average of all these features. And a couple of them show that, okay, this is a relevant feature, which is the IP bytes that were being sent out by the device. And then a not so relevant feature was missed bytes that was present in the bro data. Then we applied our domain knowledge. We said, okay, you know what? We went back to those characteristics that we said earlier, which is, small number of destinations, up-down traffic ratios tend to be high for IoT devices versus non-IoT devices. And we sort of added that into the data, and we came up with these values. And then we again ran the preprocessor on that, and you can see there's very high correlation amongst those values. So it's just a sample, 3 of them that we added in here: up-down ratio, connection counts, and the URI field. So again, this is your engineering aspect that you apply in here so that you can then move from just raw data to engineered data, and now you know what your machine learning algorithm needs to take as an input in order to do your detection. Okay? So then we ran random forest on this data, and without the feature engineering, we actually did pretty well. Even without feature engineering, gave me a 0.76 accuracy of detecting IoT versus non-IoT, given that many number of sessions. But after doing the feature engineering, that ratio increased significantly to almost a 99% accuracy. And then we tried other techniques as well. So we did boosting, we did logistic regression, we applied k nearest neighbors, and we found that, okay, these were also fairly good. So it really depends on your data set and depends on your familiarity with these algorithms. So your choice of algorithm may vary, okay? So this confusion matrix is one of the key determiners of your accuracy, your sensitivity to false positives, false negatives, and so on. I haven't put all the math in here. There was a talk earlier about machine learning. They had a lot of math in that one. So one other curve that is kind of useful is this thing called this ROC curve, and it sort of tells you what the ratio between the false positive and false negatives are. So without feature engineering, you will see that you get this 0.76 accuracy, and that's reflected in these curves, which means that you have to tolerate a certain amount of false positive rate before you get your accuracy up. But once we did the feature engineering, that value increased significant or decreased significantly, so that you can get a very high accuracy with a very low false positive rate, and that's what we wanted. Okay, so these two curves are sort of significant when you're doing any sort of machine learning analysis. Okay, so from a machine learning perspective, data is everything. So multiple people have talked about this. There was a great talk at Black Hat from the engineers at Invincia, now Sophos, about how if you feed your learning algorithms bad data, you're going to get bad data out. So a lot of people don't realize how important this is. So the way you collect your data is extremely critical, and your results are going to be extremely dependent on the data that you feed it. You need to normalize your data, especially if you have data coming in from multiple sources. Normalization is a very, very critical aspect. This is another aspect that a lot of people overlook, which is the undersampling versus oversampling. Almost always, you will have an unbalanced data set. So you'll have a large quantity of let's say, IoT or a large quantity of non-IoT traffic. And then how do you then balance? Depending upon your circumstance, you may have to use undersampling or oversampling. We were lucky that in this data set that we were considering, we had an equal number of IoT and non-IoT devices in our data set. And can't stress enough on how well the engineered features are important. So we chose our engineered features in such a way that we were able to maximize our accuracy. Choice of other engineered features may not give you that, and you may not have the luxury of choosing those features that will give you that level of accuracy. And finally, there was a talk yesterday about reinforcement learning, which is even though you may have your algorithm predict wrong data for you or incorrectly, you should be able to take that feedback. Let's say your user says, oh, you know what, that was not really an IoT device and you classified it as IoT. Well, you should take that information and then feed it back into your algorithm so that you can relearn that aspect, and that's what is called reinforcement learning, and that significantly improves detection. So it improves detection it's been shown to really work well. Okay. One little side note on detection versus identification. So far we've talked about IoT detection. So we can detect IoT. But what about actually identifying it? So I can say, okay, I have an IoT device, that is an IoT device, but can you tell me that this is a Nest thermostat? Or can you tell me that this was a TCP light bulb that actually got connected into my network? It's a little harder, and identification requires a lot more contextual information about that data. But actually it's possible, and we're getting there, okay? That's something that we're working towards. There are bro fields that you can use to extract that information. The user agent is a great field. It generally gives you a lot of information about what kinds of applications are actually running and connecting to the net if that data is available. MAC address mapping, that's a great way to actually figure out what the device is. Almost all manufacturers are given blocks of MAC addresses, so you can actually do a quick lookup and see if your device falls into one of those categories. So again, it's not conclusive, but these are all little tips that will get you towards that holy grail of identifying what that device is. DNS classification of the destination. So if I'm connecting to nest.com, I'm probably a Nest device. And similarly with SSL cert analysis, where a lot of data is now encrypted, and I may not have some of these other fields, you can just figure out from the cert itself. The cert was issued to Belkin, so therefore it must be a Belkin device. And you can then combine all of this and use some sort of natural language processing, for example, to actually extract out some really meaningful data about what that device actually is. So this is something that we are working on right now. And from an algorithmic perspective, there are some great algorithms out there. K-means and hierarchical clustering are really, really good fits for clustering and classification. Just a little sidebar. Okay, so let's go to IoT threat detection now. So a couple of ways to do threat detection. Generally, you can write a lot of rules and develop threat models. Threat models look for specific patterns. So you may say that, okay, if I see a large amount of ICMP traffic going out of my network within a certain period of time, then I probably have some sort of a device that is DOSing somebody, So that might be a threat model. Threat models are written very specifically, so therefore they look for very specific patterns. So the number of false positives are obviously minimized. However, they obviously won't catch everything unless you have threat models that are really extensive. And even then, the fact that you have 0 days implies that threat models they don't catch everything. So the other option is anomaly detection. And there are a lot of solutions out there today that say, okay, you know what, we will tell you every single anomaly that is in your network. But the problem with anomaly detection is that you get a lot of false positives, and so you need some sort of a person or some sort of a tool to go through those false positives and figure out what is really a threat and what is not. And so your goal is to sort of, in the case of anomaly detection, is to minimize your false positives. In the case of your threat models, is to sort of write enough models or find ways to encompass a large number of threats so that you get less number of false negatives. So what we're going to do is we're going to try and use our detection capabilities to do anomaly detection. And what is an anomaly? So an anomaly typically implies that you have some sort of a baseline or normal behavior, and an anomaly is something that is not normal anymore. So that's sort of the definition of anomaly in many a sense. And in order to do anomaly detection, you sort of need some way to identify what that normal or baseline behavior is. Okay, so that's the key. So what we're going to do is we're going to use the results from our detection stage to sort of build that baseline. Okay, and the key is those engineered features that we have, they actually tell a very good story. So if we can just enumerate all of those features, both from the raw data as well as from the engineered features list that we computed, that actually gives you a very good sense of what the baseline feature of the IoT devices are. So some example, just a quick example of what that might look like is that, so the Nest thermostat, communicates with just 2 destinations per day. Up-down ratio generally on an average is 4.32. The number of sessions per day is about 265, and it only uses port 11095 to communicate with. So that's like your baseline behavior of your Nest thermostat. Again, I'm just giving you a small sample of attributes over here. You can expand that out significantly to include everything from periodicity and so on. So you can really expand on that list. And similarly, I've got another example using the Belkin Wemo device, which is also on a 24-hour baseline. Okay, so going back to IoT threat detection then, so you can either write rules now to detect threats. This is kind of hard, as I mentioned before, or write anomalous pattern rules and then hunt for it. So as I mentioned, with anomaly detection, all these anomalies that come out, you have to sort of then go back and figure out from a contextual perspective whether it's a threat or an anomaly. What if we were to be able to use machine learning for this? So what we do is we summarize the baseline features, and then we can train these, we can build models that take these baseline features, compute various threat models, and then sum them together and train them with that. And once you train the machine learning algorithm, we use random forest here, we can then test out to see if these results actually work out pretty well or not. And we used a large number of PCAPs from this site called stratosphereips.org. They maintain a very large number of network PCAPs on different types of threats, DDoS, Trojans, malware, and so on. And they have ready-made Bro capture logs as well, which makes it really easy then. So you don't have to really run it through a Bro sensor and extract that data out either. So this combination is what we used in our experiment. And then what did we get? From a result perspective, on a per session basis, we actually got very, very, very good accuracy, but we did miss out a few. And again, this data seems like it is very, very accurate, but even with the per session detection, we did miss a few. So we missed about 46 and 35 sessions that were misclassified amongst 33,000. But when we were able to go to a 5-minute detection interval and summarize the data, we got complete classification. So which means that if you were to wait a little bit and aggregate the data out, and you can see the number of sessions getting diminished over here, the detection rates improve significantly. So what do our results say? It says that you get very high accuracy in determining just these common threats. Again, we didn't run it through every single threat. We looked at IoT, what might be some of the common threats associated with them, ran it against that, and those are our results. And increasing the detection time obviously improves the accuracy further. So from a closing perspective, I'm really excited about machine learning and what the applications are. As I said, I don't claim myself to be a data scientist, but seeing the applicability and the impact of using machine learning has been a tremendous learning experience for me. I'm still learning as well. We want to go ultimately towards even a threat identification using machine learning. I don't know of anyone who does that today, but that would be like the holy grail. And hopefully we can get there someday. So I wanted to thank, there were 2 interns who worked with us, Satya and Yi, over the summer. And that's not anonymous. The anonymous anonymous. That's just a person who didn't want to be named over here in the thank you list. So that's about it. Any questions? Yeah.
What's the source of the data? Where did it come from?
Okay, so the source of the data was a data set from one of our customers. Yep.
Are there any code examples up on your website or on your GitHub?
Yes, so we'll put there are some Python libraries that we have for this. We'll put that up on our GitHub website. If you give me your card or information, I can send that information to you. But yes, if you just go search for atomic mole, it's not up there right now, but we'll get it up there. Yes?
Is there a particular reason why you chose random forest versus other algorithms?
No particular reason. Random forest seems to work well for us with this data set. If you notice, even in the previous, in the detection phase, we did try out the other algorithms as well. Random forest, boosting, k-nearest neighbors, and so on. For some reason, random forest seems to work pretty well, and it's not just me. I think there was a couple of other talks today as well. They all seem to be focusing on zooming in on random forest. I don't know, but you can try others as well. As I said, it is very dependent on your data set and what you're comfortable with. Any other questions? Yes.
Out of the 33,000 sessions, how many IoT products did you distinguish from?
Okay, so there were a total of 18 IoT products and 16 non-IoT devices in the network. 34 in total.
Okay.
Yes.
Based on the background of the IoT characteristics that you defined, would it be feasible, or does it make sense to publish them somewhere online, like the original sources that you looked at?
Possible. There is actually a NSF-funded project at CMU where they are trying to do a behavior classification of all commercial IoT devices. And I think they're starting with like the popularity rather than claiming to have every single IoT. They're just taking like the top 100 popular IoT devices and starting with that. I've been working with them a little bit on being able to take some of their data and give them some of our data as well. So you might end up seeing our data over there.
Thank you.
Sure. Any others? Thank you very much, guys.